Hello, and welcome to the sleepy universe. As the space around you slowly grows quiet, let us begin with something very small and familiar. Something that may be resting in the palm of your hand, kept inside a box, lying still in a drawer, or passed down through generations as a silent keepsake, a piece of gold. Under dim light, it seems to belong entirely to everyday life, softly gleaming, enduring, and so familiar that we rarely stop to wonder where it truly began. But if we could trace each atom of gold backward through time, beyond the ore deposits where humans found it, beyond the layers of rock that once held it, and beyond the young earth that gathered it into its body, the journey would leave our planet behind and enter a story far more ancient one, written in darkness, gravity, and the remnants of stars that had already died. When we think of gold, we usually think of the ground beneath us. We picture deep tunnels, veins of ore running through mountains, riverbeds sparkling with golden sand, buried treasure, or the hands of a jeweler slowly shaping a piece of metal into a ring with a meaning of its own. That is the deeply human part of gold's journey, but it is not the true beginning. Earth does not create gold atoms the way a tree grows, leaves, or a flame produces smoke. Our planet is simply a place where gold was preserved after a much longer voyage. Before it became trapped in rock, gold was already present in the cloud of gas and dust that formed the solar system. Before that cloud existed, it may have drifted through the dark spaces between the stars. And farther back still, it was born in an event so violent that space-time itself began to tremble. From the quiet surface of a golden object, we will travel backward into the deep history of matter to understand how the universe created an element so heavy, rare, and enduring. The journey begins in a very young universe, where there was almost no gold, no iron in stone, no carbon in living things, and no oxygen in any breath. The first ingredients were far simpler than the world we know today. It took generations of stars, vast furnaces burning in the darkness for matter to be compressed, heated, fused, and gradually transformed into more complex elements. Even so, stellar fire has limits of its own. Some elements are too heavy to form easily during the ordinary life of a star, and gold belongs to a group of materials that require a far more extreme birthplace. That birthplace is connected to neutron stars, some of the strangest remnants in the universe. When a massive star reaches the end of its life, its core may collapse under its own gravity, compressed until matter becomes far denser than anything familiar on Earth. What remains is no longer a star in the gentle sense of something like the Sun, but a dead core smaller than a city that may still contain more mass than the Sun itself. A single neutron star is difficult enough to imagine. Two neutron stars bound together in the same system create something even stranger. Two stellar remnants circling one another in the darkness, losing energy with every orbit and slowly drawing closer, like a cosmic clock silently counting down. From a great distance, for most of that time, it may seem as though nothing is happening. There is no lasting brilliance, no sound, and no sign that ordinary eyes on a small planet could ever detect. But within that dance, the orbit is tightening. Each revolution brings these extraordinary objects a little closer, until the final distance is no longer enough to keep them apart. Their merger does more than release a new burst of light into space. It makes space-time itself vibrate, sending gravitational waves outward across the universe, through galaxies and immense regions of darkness, until they finally pass through Earth as a signal almost impossible to feel with ordinary human senses. Long after Einstein predicted that such ripples must exist, humans built instruments sensitive enough to listen for them. In 2017, a signal from the merger of two neutron stars was detected. Telescopes around the world then turned toward one region of the sky, where a fading glow revealed the signature of a kilonova. This was not an ordinary stellar explosion. Within the neutron-rich material thrown outward by the collision, atomic nuclei could capture additional neutrons at extraordinary speed, building heavy elements before they had time to decay. This is known as the R process, or rapid neutron capture process. The name may sound dry and technical, but it can be imagined more simply as an immense storm of particles, where small nuclei are repeatedly supplied with more matter until some of them eventually become gold, platinum, and many other heavy elements. Even then, the gold had not yet become a ring, a coin, or a fragment of metal hidden inside rock. It was only a tiny part of an expanding cloud of material carried outward into the space between the stars, over stretches of time beyond anything a human life can measure. Those atoms mixed with the gas and dust of the galaxy, drifted through the darkness, and perhaps became part of a new cloud. As that cloud contracted under gravity, a young star formed at its center, while the surrounding material gathered into planets, asteroids, comets, and smaller pieces of rock. In a system like this, around an ordinary yellow star, Earth took shape and preserved within itself a very small part of that much older story. Seen this way, gold is more than a precious metal. It is evidence of a universe that continually remakes itself through birth, death, collision, and dispersal. A ring, a necklace, a streak of gold in stone, or a thin layer of metal inside an electronic device may seem entirely familiar. Yet within every atom lies a history that began before the oceans, before forests, before human hands, and before any of the names we gave to the matter around us. This journey will move slowly from gold on Earth to the young universe, where almost no gold existed, from stars capable of forging many elements, yet unable to explain them all. From the birth of neutron stars to the long dance of two stellar remnants in darkness, from gravitational waves passing through Earth to the fading light of a kilonova, and then from dust between the stars back to the small planet where humans learn to treasure a shining piece of metal in their hands. Ahead of us, one gentle but profound question will guide the way. How could the death of two distant stars create something that would one day become part of the living world? The answer belongs not only to gold, it belongs to the way the universe preserves the traces of its most violent moments, carries them through time, and allows them, one day, to become something small, quiet, and close enough to rest in the palm of a hand. When a piece of gold rests in a human hand, the first impression it gives is usually something closely tied to the earth. It has real weight, a tangible surface, and a visible shine. We can touch it, weigh it, melt it, store it, or shape it into an object with a meaning of its own in our lives. That familiarity makes it easy to think of gold as something that belongs entirely to this planet, as though Earth quietly created it inside dark tunnels, beneath the pressure of stone and the heat deep underground, then left it there for humans to discover after millions of years of waiting. That view is not entirely wrong when we are talking about where gold accumulates, but it tells only the final part of the story. At the atomic level, Earth is not where gold was born. A gold deposit may lie deep inside a mountain. A grain of gold may be rounded over time by flowing river water. A vein of ore may form when hot fluids move through fractures in rock, carrying metals with them and leaving those metals behind in tiny spaces. This is geology, the history unfolding within a planet, and the way gold is gathered into concentrations rich enough for humans to extract. But the process is more like rearranging letters that already exist than creating the alphabet itself. Rock can hold gold. Hot water can transport it. Pressure, temperature, geological faults, volcanic activity, and the movement of tectonic plates can all help concentrate it into deposits. Yet none of these processes creates a gold nucleus from the beginning. They only move, gather, conceal, and occasionally expose atoms that were already present before this planet took on its familiar form. This helps us separate two questions that are often blended together. The first is where gold is found on Earth. The second is far deeper. Where were gold atoms created in the universe? To answer the first, we can talk about ore deposits, riverbeds, metamorphic rock, and mineral veins within the planet's crust. But the ground beneath us is not enough to answer the second. We must leave the mining tunnels, geological maps, and even the history of mountain formation behind. Traveling back to a time before Earth existed, before the sun began to shine, when the material of the solar system was still part of a vast cloud of gas and dust drifting among the stars. If we imagine Earth in its earliest age, we would not see the peaceful blue planet we know today. It was a world being assembled through collisions, melting, and accumulation, while fragments left behind in the disk of material surrounding the young sun continued to strike its surface. Different elements entered the growing planet during this chaotic period. Iron sank inward and helped form the core, while lighter materials remained closer to the outside. Because of its chemical properties, gold tends to follow iron when a planet is molten. So much of Earth's original gold may have been drawn down into regions far beyond human reach. Later, impacts, cooling, the restructuring of the crust, hydrothermal activity, and perhaps additional material delivered by smaller celestial bodies helped leave some gold in the crust, where human beings would eventually be able to find it. Yet no matter which path those atoms followed through geological history, they did not begin on Earth. The planet is more like a keeper of memories than their creator. It received material from the cloud that formed the solar system, then rearranged that material through billions of years of change. When miners remove gold from rock, when a river reveals a few bright grains in heavy sand, or when a jeweler softens gold in a flame, they are all working with atoms that have existed far longer than any civilization. Those atoms were once part of precellar dust. They once drifted through interstellar space. They were mixed into the material of the galaxy before a small rocky planet ever had the chance to hold them. There is an important distinction here that can easily be misunderstood. When we say that gold came from space, we do not mean that complete bars of gold once fell intact from the sky like objects in a myth. Gold did not travel through space as finished jewelry, nor was it delivered to Earth as a gift that had already been shaped and cast. It existed as atoms mixed into dust, rock, small fragments of matter, and the tiny particles within the cloud that formed the solar system. Those atoms were then drawn into the process of planetary formation. They were buried, melted, pulled downward, carried upward again, separated, and eventually concentrated wherever geological conditions allowed. What humans call gold on Earth is the result of two overlapping histories. A cosmic history that created the atoms, followed by a geological history that gathered them into places where they could be found. Seen in this way, a gold deposit is no longer the beginning, but a late stopping point in a very long journey through matter. The bright veins running through stone are simply where the story becomes close enough for human eyes to recognize. Before that, it had already passed through far greater scales, through the lives and deaths of generations of stars, through explosions or collisions capable of scattering heavy material into space, through the slow mixing of matter within the galaxy, and through the collapse of a cloud of gas and dust that carried elements left behind by earlier events. Each tiny grain of gold resting silently in rock can be seen as a very late period, at the end of a sentence written long before there were mountains, oceans, living things, or hands capable of digging into the ground. What makes gold remarkable is not only its rarity in Earth's crust, but also the difficulty of producing it at the nuclear level. Light elements such as hydrogen and helium appeared very early in the universe. Elements including carbon, oxygen, neon, magnesium, and silicon can be created during the lives of stars through nuclear fusion. But gold has a more complicated history. Its nucleus is much heavier, requiring neutron-rich conditions and enormous amounts of energy to form. Earth does not provide such an environment. The planet's interior is extremely hot, and its pressure is immense compared with anything in everyday human life, but it is still not the kind of place where gold nuclei can be built from smaller particles in the way the universe once produced them during extreme events. This does not make Earth any less beautiful. On the contrary, it makes our planet even more fascinating. Earth does not need to create everything itself in order to be a world rich in matter. It is a gathering place, a small planet built from the materials of stories far older than its own. In stone lies the memory of fire, In water lies the memory of ice and vapor. In living bodies lies carbon once forged inside stars. And in gold lies the trace of rarer environments, where the universe could produce heavy elements in ways that the quiet ground beneath us can never repeat. When we place a gold ring beneath soft light, its surface reveals none of this. It simply reflects a small, warm, steady glow that seems almost unchanged. That silence makes gold feel as though it belongs entirely to the present, to the person holding it, to the memory attached to it, and to the value humans have given it. Yet beneath those human meanings lies a deeper layer, where gold is no longer a symbol of wealth or commitment, but a tiny sample of cosmic history. It reminds us that the things closest to us do not always begin nearby. An object resting in the hand may carry within it the journey of stellar clouds, dead stellar cores, distant collisions, and processes so slow that no human lifetime could ever witness them from beginning to end. The question now begins to expand beyond Earth. If our planet merely preserved the gold, if rock only concealed and concentrated it, and if ore deposits are simply the final chapter in the geological history of atoms that already existed, then where in the universe were those atoms actually created? The answer cannot be found inside a mountain, a river, or the deep layers of rock beneath our feet. It leads us back to the young universe, when many of the elements familiar to life had not yet fully appeared, when matter was far simpler than it is today, and when the first generations of stars began transforming the darkness into immense furnaces for creating the elements. Before there was golden rock, before there was iron in the cores of planets, before there was carbon in living bodies or oxygen in the first breaths of life, the universe passed through a very different age. It was not yet filled with shining stars, spiral galaxies, rocky planets, or clouds of dust rich in heavy elements. In that distant beginning, matter was far simpler. If we could look back with a slow and patient imagination, we would see no gold glittering anywhere. We would not find familiar metals embedded in stone, mineral dust, veins of ore, or any solid world capable of preserving a rare element. Nearly the entire story of matter had begun with only the lightest ingredients. After the Big Bang, the universe did not immediately contain all the elements we know today. During the first few minutes, while temperatures were still extraordinarily high, fundamental particles gradually joined together to form simple atomic nuclei, mostly hydrogen and helium, along with a very small amount of lithium. These names may sound familiar from science, but in the story of gold, they are like the first notes of a piece of music that had not yet taken shape. Hydrogen is the lightest and simplest element, requiring only one proton in its nucleus. Helium is slightly heavier, but still far removed from the complex elements that would appear much later. Gold, with its heavy nucleus containing many protons and neutrons, was something the young universe could not produce under those early conditions. This means the universe was not born with gold. It had to pass through a very long period of development before gold could exist. The idea may sound almost like something from ordinary life, but it describes the history of matter surprisingly well. The early universe was a place with very few kinds of material. The first building blocks were present, but there were no builders, no furnaces, no intense pressures, and none of the extreme environments needed to transform that simplicity into abundance. For carbon, oxygen, silicon, iron, gold, or platinum to exist, matter had to enter stars, endure immense temperatures and pressures, and pass through the lives and deaths of many generations of celestial bodies. Everything around us today, from the stone beneath our feet to the blood within our bodies, belongs to a universe that stars have gradually transformed over time. There is an easy misunderstanding that can arise here. We might assume that because the universe began in an event of extraordinary heat and power, every element must have been created at the beginning, but high temperatures do not automatically produce every complex structure. During those first moments, the universe was expanding too quickly. The conditions needed to form atomic nuclei lasted only a very short time. Light nuclei could take shape, But heavier ones did not have enough time or a sufficiently stable environment to be built step by step. The rich variety of the periodic table, which people encounter in textbooks as a neatly ordered list, is actually the result of many successive chapters in cosmic history, not a complete gift that appeared the moment the universe began. We can picture the young universe as a room stretching endlessly in every direction, yet containing almost no furniture. Only a few simple kinds of material drifted throughout that enormous space. There were no planets for them to fall upon, no solid surfaces for them to cling to, no mineral deposits, no oceans, and no grains of gold resting quietly inside stone. Light and matter were gradually separating from one another. Space continued to expand, and clouds of light gas waited silently for gravity to begin its long work. It was gravity, rather than the original chaos, that would start gathering matter together, drawing slightly denser regions of gas into larger clouds, and slowly preparing the way for the first stars. Those first stars held a very special place in cosmic history because they were the earliest environments where the universe could begin transforming matter in a deeper way. Before they appeared, most material simply drifted through the darkness as light gas. When clouds of gas grew large enough and collapsed, the temperature inside them rose, the pressure increased, and eventually nuclear fusion began. Hydrogen was pressed into helium, energy was released, and light emerged. A star was born. From the outside, this may have marked the moment when the universe began to grow brighter. But at the level of the elements, it was also the moment when the cosmos gained its first factories for turning light nuclei into heavier ones. Even so, it is important to move slowly here. Stars do not transform hydrogen directly into gold. They operate through different layers, conditions, and stages of their lives. A star like the Sun spends most of its lifetime converting hydrogen into helium. More massive stars can go farther, producing carbon, oxygen, neon, silicon, and eventually approaching iron within their cores. Each stage requires higher temperatures, greater pressure, and a more complex internal structure. Matter does not leap from simplicity to rarity in a single step. It follows a long path, with each generation of stars adding a little more chemical richness to the universe. This is why gold is special at the most fundamental level of its story. It is not rare only because humans have difficulty finding it underground. It is rare because the universe itself does not create it easily. Building a gold nucleus requires far more protons and neutrons than forming a light element. The reactions that occur during the ordinary lives of stars do not always provide a suitable path. Even when a very massive star reaches the end of its life, producing elements heavier than iron is no longer as simple as burning through another layer of fuel. The universe must turn to other processes more violent, more fleeting, and far richer in neutrons where matter can capture particles rapidly before it has time to decay. Seen from the scale of everyday life, this makes a golden object seem even stranger. It is not merely rare because it was buried deep underground, nor simply valuable because it is durable enough for humans to preserve. It was rare before there was any ground to bury it. It was extraordinary before there were hands to mine it. The early universe did not contain ready-made gold atoms waiting to be gathered into planets. Those atoms had to be created later, in environments Earth could never reproduce, through processes far beyond the heat of volcanoes or the pressure of deeply buried rock. In gentler terms, we might say that the young universe had not yet learned how to make gold. It possessed only the first ingredients, a very limited range of atomic nuclei, vast amounts of space, and an immense future still ahead. It had to wait for clouds of gas to collapse, for the first stars to ignite, and for massive stars to live more quickly, die sooner, and return their transformed material to space. It had to wait for new generations to be born from the remains of those that came before. With each cycle, the universe became not only brighter, but chemically richer. More complex elements gradually appeared, mixed into gas and dust, entered later stars and planets, and, much farther into the future, became part of life. Within this larger picture, gold is a sign of a much later stage of cosmic maturity. It tells us that matter had already passed through many transformations before becoming complex enough to form heavy elements. It also reminds us that everything familiar around us has its own history within the galaxy. A wooden table requires carbon. A drop of water requires oxygen. A living cell depends on many different elements created by generations of stars. A piece of gold requires rarer conditions, still denser streams of neutrons, and more extreme moments. In this way, the story of gold is not separate from the story of how the world came to be. It is simply one especially deep branch of the same history of matter. As the universe emerged from its early simplicity, stars became the first places where matter truly began to change. They did more than illuminate the darkness. They carried out a quieter task, turning light nuclei into the foundations of heavier elements, then returning some of those results to space when their lives ended. Without stars, the periodic table would be almost empty compared with the world we know. Without those immense furnaces, there would be no complex rocks, no planets like Earth, no living bodies, and no questions about gold for humans to ask in a quiet room. And yet, stars are not the complete answer. They opened the first door, created many essential elements, and made the universe richer, but their limitations will lead us deeper into the journey. To understand gold, we must enter the furnaces inside stars and see how they create matter, why they can produce carbon, oxygen, silicon, and iron, yet struggle to form heavier elements such as gold. From there, the story will begin to cross the boundary between the ordinary light of stars and more violent events, where the universe finds its rare pathways for building the heaviest atomic nuclei. When the first generations of stars began to shine, the universe gained more than light. It gained its first places hot enough, dense enough, and stable enough for matter to be transformed from within. Before then, hydrogen and helium dominated nearly the entire chemical landscape of the cosmos. They drifted through vast, simple clouds of gas, carrying none of the richness later found in rock, water, metal, or life. As gravity pulled those clouds inward, their centers gradually grew hotter. Pressure increased. Matter became more tightly compressed. At a certain threshold, hydrogen nuclei began to fuse, forming helium and releasing energy. A star was born not only through the light it sent outward, but through a quieter process deep inside, the transformation of light elements into the foundations of heavier ones. A star can be imagined as an immense furnace, but only if we remember that it is nothing like an ordinary fire. On Earth, fire can burn wood, heat metal, and under special conditions even melt rock, but it cannot turn one element into another. A flame on a stove or inside a forge merely rearranges molecules, breaks chemical bonds, and changes matter from solid to liquid or from cold to hot. Inside a star, the story reaches much deeper. There, temperatures and pressures are high enough to force atomic nuclei close together, overcome the natural repulsion between their positive charges, and fuse into new nuclei. When that happens, matter does not simply change its form. It changes its identity at the atomic level. For most of a star's stable lifetime, hydrogen is its primary fuel. Hydrogen nuclei combine to form helium, and the energy released by this process helps the star resist its own gravity. Gravity is always trying to pull all of the material inward, compressing the star into a smaller space. Light and pressure, generated by nuclear reactions, push outward in response, creating a balance that can last millions, billions, or even tens of billions of years, depending on the star's mass. A star, then, is not a ball of fire burning in the everyday sense, but a long negotiation between the inward pressure of gravity and the energy produced in its core. Within that negotiation, matter is slowly cooked at its deepest level. For small and medium-sized stars, the journey of element making does not extend very far. A star like the Sun may spend most of its life converting hydrogen into helium. As the hydrogen in its core gradually runs low, it enters other stages, expands, changes color, and under certain conditions produces additional elements such as carbon and oxygen. But it does not have enough mass to pass through the entire chain of reactions, leading to much heavier elements. Our sun is essential to life on Earth, but it is not a factory capable of producing gold. Its cheese warms the oceans, shapes the climate, and nourishes plants. Yet the gold atoms in the solar system were already present before the sun settled into the stable state we see today. Massive stars tell a more violent story. Because of their greater mass, they compress their cores more strongly, raising internal temperatures and allowing nuclear reactions to proceed farther. After hydrogen comes helium. After helium, during later stages, may come carbon, neon, oxygen, and silicon. Each layer of fuel burns under more extreme conditions than the one before it. Near the end of its life, the interior of a massive star can resemble a cosmic onion with different layers of material surrounding the core. Hydrogen remaining in the outer regions, helium deeper within, followed by carbon, oxygen, silicon, and finally a central region approaching iron. The image does not need to function as a precise technical diagram to reveal something important. A massive star does not forge matter in a single step. It moves through many layers, many stages, and many limits. Iron marks a very special stopping point in this story. For elements lighter than iron, fusion can generally release energy, giving the star something like another breath with which to resist gravity. Once the process reaches iron, that advantage largely disappears. Fusing iron into heavier elements does not easily provide the star with additional energy. It is as though the furnace has reached a material that, if compressed in the same way, no longer feeds the fire, but instead demands payment from the energy that remains. This is why massive stars cannot simply continue burning through one layer after another and calmly produce gold as the natural final product of an assembly line. This boundary makes the story of gold clearer. Stars truly are responsible for creating many essential elements. Without them, the universe would lack carbon for life, oxygen for water and breath, silicon for rock, calcium for bones, and iron for planetary cores and living blood. But gold lies on the other side of a more difficult threshold. A gold nucleus is far heavier than iron. To build one, the universe cannot rely only on the stable lifetime of an ordinary star. It needs another pathway, one in which nuclei can capture neutrons very quickly and move beyond barriers that ordinary fusion cannot easily cross. We can pause for a moment within the image of these stellar furnaces. Deep inside a massive star, nearing the end of its life, different layers of fuel are burning at different depths, each preserving part of the history of nuclear reactions. Moving inward, the material becomes heavier, the temperature rises, and the duration of each stage grows shorter. Hydrogen may burn for millions of years. The final stages, such as the conversion of silicon toward iron, may unfold in a time far shorter than the star's entire lifetime. A massive star spends most of its existence in a state that seems almost stable, but as the end approaches, changes deep inside begin to accelerate, as though the history of matter is being compressed into its closing chapters. That compression matters not only to the star itself, it also prepares the star to return material to the universe. When a massive star can no longer maintain its balance, its core may collapse, while its outer layers are thrown into space in a supernova explosion. Elements created during the star's life, along with some formed during that violent final moment, are scattered into the space between the stars. Through deaths like these, the universe does not keep complex matter locked forever inside stellar cores. It spreads that material outward and mixes it into clouds of gas and dust, allowing later generations of stars and planets to form from ingredients richer than those that came before. But a supernova should not be treated as the only answer to the origin of gold. For a long time, Stellar explosions were considered especially strong candidates for producing many heavy elements. They certainly play a major role in chemically enriching the universe. They create and disperse many elements, while leaving behind strange remnants such as neutron stars or black holes. Yet for the very heavy elements formed through rapid neutron capture, modern science shows that neutron star collisions are an especially important source. In other words, massive stars prepare the way, supernovae return matter to space, and some of the stellar remnants left behind may later take part in rarer events where gold can be produced more efficiently. This chain of events makes the lives of stars an essential part of the story, even though an ordinary star is not a complete environment for making gold. Without generations of massive stars, there would be no dead stellar cores. Without the deaths of giant stars, there would be no neutron stars. Without neutron stars, the neutron-rich collisions we are approaching could never occur. Gold, then, does not come from a single isolated moment, but from a long sequence. An initially simple universe, light gases collapsing into stars, stars forging matter, massive stars dying, their remnants continuing to exist, and, in a few very rare cases, two of those remnants finding each other in an orbit that grows steadily tighter, returning to a golden object beneath soft light. It may seem even quieter once we understand this. It does not need to shine brightly to carry an immense history. Its atoms were not made by a mountain, nor were they cooked in the flame of a jeweler. They belong to a much longer story, one in which stars served as the universe's first metalworkers, creating many of the fundamental ingredients of matter before reaching limits they could not cross. Those limits make gold more profound. It is not simply a product of starlight, but something that also requires the darker chapters of stellar fate, where death does not end the story, but becomes the condition for another kind of creation. From the furnaces of stars, the journey now moves toward the remnants left behind after their fires have gone out. When a sufficiently massive star passes through its final stages, its core cannot remain balanced forever. Matter is pulled inward and compressed to densities beyond human intuition, while the outer regions may be blasted into space. One of the strangest possible results of that death is a neutron star. It is no longer a furnace for forging elements in the familiar sense, but the compressed core of a star that has died unbelievably small, unimaginably massive, and so rich in neutrons that it will become the central figure in the later story of how gold is made. After passing through the furnaces of the stars, the story of gold begins to reach a very deep boundary. Stars can accomplish things that seem almost impossible, turning hydrogen into helium, creating carbon, oxygen, silicon, and iron, then returning those elements to space when their lives come to an end. Through generations of stars, the universe ceased to be a place made only of light gases and darkness. It gradually gained rock, dust, metals, planets, water, and eventually the conditions in which life could emerge. But gold lies farther along the path of building the elements. It requires more than intense heat. It needs a special kind of environment where matter is flooded with an enormous number of neutrons over a very short period of time. To understand why gold is so difficult to create, we need to look at the atomic nucleus in the simplest possible way. Every atom contains a tiny central core called the nucleus. Inside it are protons and neutrons. Protons carry a positive electric charge, and their number determines which element the atom is. A nucleus with 1 proton is hydrogen. With 6, it is carbon. With 26, it is iron. Gold has 79 protons in its nucleus, far more than the lighter elements familiar to us. But protons do not stand alone. They need neutrons beside them to help make the nucleus more stable. Heavy elements require large numbers of neutrons as well, making the construction of a gold nucleus an extraordinarily difficult task on a cosmic scale. One way to picture this is to imagine light elements as small houses built from only a few bricks, while gold is a massive and complicated structure, requiring many pieces of material to be placed correctly under extremely harsh conditions. It is not enough to gather a few particles and wait for them to become gold. Positively charged protons repel one another, making it difficult to force them into the same nucleus. The fusion reactions inside stars can overcome this barrier for many lighter elements because of their immense temperatures and pressures. But as nuclei become heavier, fusion grows less favorable, especially beyond the region of iron, where creating still heavier elements no longer releases energy as easily as it once did. This is where neutrons become important. Unlike protons, neutrons carry no electric charge. They can enter a nucleus without facing the same kind of electrical repulsion. When a nucleus captures another neutron, it becomes heavier. Then, in some cases, a neutron inside it can transform into a proton through beta decay. When the number of protons changes, the element itself changes. Through a sequence of neutron capture followed by decay, the universe can build heavier nuclei along a path different from ordinary fusion. Protons do not need to force their way directly into the nucleus at the beginning. Neutrons enter first, then gradually alter the identity of the nucleus from within. Two forms of neutron capture are commonly discussed in astrophysics. One happens more slowly and is known as the S process, or slow neutron capture process. It can occur during certain stages in the lives of aging stars, where nuclei have time to capture one neutron and become more stable before taking in another. This pathway creates many heavy elements and makes an important contribution to the chemical richness of the universe. But to produce some of the heaviest elements, along with large numbers of nuclei far from stability, the cosmos requires a more violent situation. This is the R process, or rapid neutron capture process, in which nuclei are exposed to such a dense flood of neutrons that they can capture many of them in succession before they have time to decay. The name R process may sound dry, but the image behind it is powerful. Picture a small nucleus caught in a rain of neutrons so dense that there is almost no pause between impacts. It captures one neutron, then another, then many more, within an extremely brief span of time. The nucleus becomes heavily enriched with neutrons and cannot remain stable for long, but that very instability opens the way for beta decay. Some of its neutrons transform into protons. The number of protons rises, the element changes, and the nucleus gradually moves toward heavier regions of the periodic table. Through this chain of capture and decay, elements such as gold, platinum, and uranium can emerge. The conditions required for the R process are not merely hot. They must be unusually rich in neutrons. Large numbers of free neutrons must be present within a region of rapidly changing matter. The density, energy, and speed must be great enough that nuclei do not capture only a few neutrons and stop, but are driven far from stability before they have a chance to settle. Places like this are not common in the universe. They are nothing like the surface of a planet, the hot interior of Earth, or the flame of an ordinary laboratory. They belong to extreme events connected to the deaths or remnants of stars, where matter is torn apart, compressed, expelled, or mixed under conditions that the stable life of a star cannot sustain for long. The beauty of the R process lies in the fact that it is both violent and brief. A star may burn for millions or billions of years, yet the creation of many heavy elements, through rapid neutron capture, can unfold in a moment compared with the lifetime of a star. During that interval, matter passes through an intense transformation. Then, as the environment cools and the nuclei begin to settle into more stable forms, the newly created elements remain like traces of a storm that has already passed. From this perspective, gold is not a product slowly baked in a furnace over millions of years. It is more like a signature written very quickly by the universe under conditions that almost nowhere else can reproduce. Hearing about such a violent process, it is easy to imagine that science has already resolved every detail. The reality is more subtle. Scientists understand the general principles of rapid neutron capture quite well. They understand why it requires a neutron-rich environment and how it can create many heavy elements. but the exact contribution of different sources to the total amount of gold in the universe is still being studied. For many decades, supernovae were considered important candidates. Later, observations of neutron star collisions, especially the event detected in 2017, showed that these mergers truly can create and release large quantities of heavy material. The picture, then, is not a closed answer, but a map that becomes clearer with every discovery. To remain precise, we can say that neutron star collisions are among the important sources directly linked by observation to the production of heavy elements through the R process. This statement is strong enough to preserve the wonder of the subject without turning a still developing area of science into an absolute claim. Gold may have more than one origin story in different cosmic environments, but neutron star mergers have given humanity an especially clear image. Two dead stellar remnants coming together, neutron-rich matter being thrown outward, the light of a kilonova appearing, and heavy elements forming within the expanding debris. From the perspective of someone resting quietly in a dark room, the R process may feel unimaginably distant. It occurs in places no human can reach, during moments invisible to ordinary eyes, through particles far too small to picture directly. But if we reduce the entire idea to a single image, we might think of an invisible rain of neutrons falling not onto the ground, but into the nuclei of atoms. Each added particle makes the matter heavier and more unstable. Through the transformations that follow, the identity of the element begins to change. Within that brief chaos, the universe builds atoms that will later rest quietly in rock, in planets, in technology, and in human memory. The path to gold, then, does not follow everyday intuition. On Earth, people dig downward to obtain it. In geology, we look to ore veins, faults, hydrothermal activity, and the history of rock. But to understand how gold first came into existence as an element, the search must turn upward toward the sky, then travel beyond the ordinary light of stars. We must look for places filled with dense populations of neutrons. We must examine what remains after stars die. We must follow events that do more than shine, events that also make space-time itself tremble. From a metal held in the hand, the story suddenly opens into some of the deepest laws of matter. And it is here that neutron stars begin to move into the center of the journey. If gold requires a neutron-rich environment, few objects in the universe carry a more fitting name. Neutron stars are the remnants of massive stars, where matter has been compressed so intensely that protons and electrons combine to form neutrons, leaving behind a stellar core that is small, dense, massive, and profoundly strange. A neutron star is not an ordinary cloud of matter. It is what remains after a giant star can no longer resist its own gravity. Once we understand how such an object is born, we can begin to understand why the collision of two neutron stars can create one of the most neutron-rich environments the universe provides for forging heavy elements. To reach the story of neutron stars, we must return to the life of a massive star. Not every star ends in the same way. A small star may fade more gradually, leaving behind a white dwarf core that slowly cools over time. A star like the Sun is also not massive enough to become a neutron star after it dies. But for stars many times more massive than the Sun, the final stage of life does not unfold like a lamp slowly going dark. They live by resisting their own gravity, using the energy generated in their cores to keep their immense mass from collapsing inward. As each layer of nuclear fuel is exhausted, that balance becomes increasingly fragile, until the core no longer has a familiar way to support the weight pressing down from above. For most of its life, a massive star is like a city of fire with many layers inside. In one region, hydrogen fuses into helium. In another, helium can help form carbon and oxygen. Deeper still, reactions at higher temperatures create heavier elements until the core approaches the region of iron. But iron is no longer a useful fuel in the way lighter elements once were. When the core becomes dominated by nuclei such as iron, fusion can no longer easily release the energy needed to resist gravity. The The star still carries an enormous mass pressing down on its center, while the internal pressure supporting it weakens rapidly. The entire vast structure begins to approach a limit that ordinary starlight can no longer overcome. The collapse of the core is one of the most extreme movements matter can undergo during the life of a star. The central region is compressed at tremendous speed. The outer layers have not yet had time to respond to what is happening, while the core is already falling inward beneath its own weight. As the density rises, electrons are forced close to protons. Under these conditions, many protons and electrons combine to form neutrons, releasing neutrinos in the process. Neutrinos are particles that interact only very weakly with matter, allowing them to escape from dense regions that light cannot easily cross. We do not need to follow every technical detail of this process. The central image is enough. Matter that once belonged to the core of a star is being compressed until its familiar atomic structure is almost erased, leaving behind an object unimaginably rich in neutrons. Once the core has been compressed to an extreme limit, it cannot continue shrinking in the same way forever. Matter enters an unusual state in which neutrons are packed tightly together, producing a form of quantum pressure that resists further collapse, at least if the core is not massive enough to cross the threshold and become a black hole. What remains may become a neutron star, an object so small that its size would seem almost insignificant beside a planet, yet one that can contain more mass than the Sunday. Meanwhile, the star's outer layers are blasted into space in a supernova, carrying material forged during the star's lifetime and scattering it into the interstellar medium, where later generations of stars will form from ingredients richer than those that came before. A neutron star, then, is more than the corpse of a star. It is the core left behind after gravity has pushed compression almost as far as it can go, without crossing the boundary into a black hole. Such an object may be only a few dozen kilometers across, roughly the scale of a large city, yet contain more mass than the Sunday. That image is difficult to hold in the mind because it brings two very different scales together in one place, as small as an urban region, yet as heavy as a star. A teaspoon of neutron star material could have a mass far beyond anything familiar on Earth. The comparison is not meant to overwhelm, but to gently suggest that matter in the universe can exist in states so unfamiliar that everyday experience is no longer enough to picture them. The surface of a neutron star is nothing like the surface of a planet. It has no oceans, forests, mountains, or atmosphere in any familiar sense. Gravity there is extraordinarily strong. Its magnetic field can be violent. Matter is arranged in states that laboratories on Earth can reproduce only in very limited ways through theory, observation, and particle accelerators. The interior of a neutron star remains an area of deep research because humans cannot look directly into its core. Models suggest that matter there may pass through several different layers of structure, from a crust rich in atomic nuclei to deeper regions where neutrons dominate. Some details remain uncertain, but one point is secure enough for this journey. Neutron stars contain matter that is extremely dense and rich in neutrons, making them central to the story of the heavy elements. Not every neutron star sits quietly in the darkness. Some rotate very rapidly and emit steady beams of radiation like cosmic lighthouses. When one of those beams sweeps across Earth with each rotation, we observe a pulsar, a neutron star that appears to pulse. The regularity of pulsars once astonished scientists because the signals arriving from space were so precise that they initially seemed almost artificial. Later, researchers understood that the rhythm came from an extraordinary rotating object whose powerful magnetic field directs beams of radiation outward. The lighthouse image makes a neutron star feel less abstract. A small, massive, dead stellar core can still send its rhythm across the darkness of space. The existence of pulsars has also allowed humanity to understand neutron stars in a particularly beautiful way. We cannot travel close to these objects, place instruments on their surfaces, or bring a piece of neutron star material back to a laboratory. But we can listen to the rhythm of their rotation, measure how their signals change, track the tiny slowing of their spin over time, and observe systems in which two compact objects orbit one another. From those distant signs, astronomers build a picture of their mass, radius, magnetic field, orbit, and even the way they lose energy. The science of neutron stars is therefore more than a theory about stellar death. It is also the art of reading very faint signals from objects that can never be touched. Another important point lies in the way neutron stars can form within binary systems. Many stars in the universe do not live alone as our sun does. They are born in pairs or groups, bound together by gravity and orbiting a shared center. If both stars in a binary system are sufficiently massive, each may eventually reach the end of its life, explode, and leave behind a neutron star. This process does not easily unfold in a stable way. A supernova can kick the binary out of its former orbit or even separate the two objects forever. Only in certain cases, after periods of mass transfer, core collapse, and stellar explosion, do the two remnants remain gravitationally bound, continuing to orbit one another in the darkness. When a system containing two neutron stars survives, the story shifts from the individual death of a single star to the shared fate of two remnants. They do not necessarily collide at once. In fact, they may continue orbiting each other for an immense span of time. With every orbit, they release a very small amount of energy in the form of gravitational waves. That loss causes the orbit to shrink gradually, almost too slowly to notice over a short period. But across millions or billions of years, the distance between them can narrow until merger becomes unavoidable. Two dead stellar cores, born in separate explosions, eventually enter a shared motion, preparing for an event capable of producing light, gravitational waves, and newly formed heavy matter. This is why neutron stars form a bridge between the lives of stars and the origin of gold. A neutron star is not a simple furnace in which the gold of a ring is heated into existence. It is what remains after a massive star has died, a reservoir of neutron-rich matter, compressed by gravity into an extraordinary state. When it meets another neutron star in a collision, some of that material can be released into space under conditions suitable for the R process. In other words, gold requires more than the fire of stars. It requires what remains after that fire has gone out, the compressed core of a dead star, and a long orbital history that allows two remnants to draw close enough to meet. Seen across the entire sequence, the death of a star is no longer a simple ending. It is a change of role. The star once shone for ages, forged elements in its core, and resisted gravity with energy of its own making. At the end of its life, the outer layers are returned to space, while the core contracts into an object of almost unimaginable compactness. If it is alone, it may slowly lose its spin in the darkness, pulse like a distant lighthouse, or quietly cool over cosmic time. If it has a companion of the same nature, the two may enter a much longer dance, where every orbit carries them closer to an encounter that will make space itself tremble. The transition from a solitary neutron star to two neutron stars within the same system is a crucial one. A single neutron-rich object helps us understand matter under extreme conditions. Two such objects locked together provide a way for that material to be released, mixed, and thrown outward, becoming the raw material for heavy elements. The journey cannot end at the moment a neutron star is born. It must continue into the darkness between two stellar remnants, where there is no brilliant fire like the one they carried while alive, yet gravity, motion, and the steady loss of energy remain, sustaining a long and quiet orbit until the final distance between them disappears. A single neutron star is enough to slow the imagination, but two neutron stars existing within the same system open an entirely different story. They are not simply two extraordinary objects placed beside one another in space. They are what remains of two stars that once lived, burned through their fuel, and shone with light of their own before each passed through a violent death and became a compressed stellar core. If gravity still holds them together after both explosions, they will continue orbiting one another in the darkness, like two small remnants of former suns following a rhythm written long ago into the structure of their orbit. For a system containing two neutron stars to form, many conditions must unfold in sequence in an exceptionally rare way. It may begin with two massive stars born close together within the same cloud of gas. Bound by gravity, they circle a common center and grow within the same region of space. The more massive star usually lives faster, consumes its fuel more intensely, and reaches the end of its life first. When it explodes and leaves behind a neutron star, the binary system can be violently disturbed. The orbit changes. Matter is thrown outward. The newly formed remnant may receive a powerful kick from the explosion, strong enough to tear the entire system apart. Only if the gravitational bond survives can the first neutron star continue orbiting its companion, which is still alive. Eventually, the second star reaches the end of its own life. It may expand, exchange matter with the neutron star beside it, lose its outer layers, and then undergo core collapse in another explosion. Once again, the orbit is tested. If the blast is too uneven, if too much mass is lost, or if the kick is too powerful, the two objects may separate forever. Yet in a small number of cases, the system remains intact after both deaths. Two neutron stars, small, massive, and dense, circling an invisible point between them. From the perspective of cosmic time, they are like a pair that has passed through two stellar storms without being pulled apart. Their motion is not like the orbit of planets around the Sunday Earth follows a path so stable that humans use it to measure years, seasons, and the rhythm of daily life. Two neutron stars in a much tighter system carry within their orbit a quiet and continuous loss. They circle each other at tremendous speed and may complete an orbit in far less time than the familiar paths of planets. With every revolution, the system releases a small amount of energy in the form of gravitational waves. That energy travels away, carrying with it a tiny portion of the orbital motion. As the system loses energy, the distance between the two neutron stars slowly begins to shrink. The change is so gradual that, viewed over a brief moment, everything might appear almost motionless. For most of this long period, no great flame erupts. No bright cloud appears like a visible nebula. The two compact stellar remnants may orbit through darkness for millions or billions of years, quietly losing energy in a way human eyes cannot directly see. But physics continues its work. Each orbit becomes slightly shorter. The circling grows a little faster. The distance narrows by another almost imperceptible amount. The system resembles a silent clock whose hands not only measure time, but gradually draw the two objects closer together. Gravitational waves give this long dance a deeper meaning. In general relativity, gravity is not merely an invisible pulling force in the way everyday intuition might suggest. It is connected to the shape of space-time itself. Massive objects curve space-time around them. When two extremely massive bodies orbit one another, especially objects as small and dense as neutron stars, their motion can create ripples that travel outward. These ripples are extraordinarily weak by the time they reach Earth, yet they carry information about the orbit, the masses, and the final moments of the system. Throughout most of the binary's life, gravitational waves are the way it quietly leaks energy into the universe. We might picture the space around two neutron stars as an immense surface of water. A heavy stone resting still can create a depression, while two very heavy stones moving around one another would send faint ripples outward. The comparison is not exact, because space-time is not water, and gravitational waves are not waves across a lake. Even so, the image gently suggests that the motion of two stellar remnants does not remain confined to the place where it occurs. It sends traces outward, extremely faint and delicate, yet real enough that one day human beings could measure them as they pass through our planet. As the distance between the neutron stars decreases, their orbital dance grows faster. They do not simply move toward each other in a straight line. They spiral inward, like two small leaves caught in an invisible current, circling more rapidly as they approach the center. During the early stages, This process may last so long that no living thing could witness it from beginning to end. The final stage unfolds far more quickly. The orbital rhythm accelerates, the gravitational waves become stronger, and energy is lost at an increasing rate, as though a cosmic clock that remained quiet for billions of years has suddenly begun racing through its final turns. This acceleration produces the characteristic signal that gravitational wave detectors can recognize, a rising tone that grows both faster and stronger before the two objects merge. In the story of gold, the long period before the collision is just as important as the final moment. If we look only at the merger, it may seem as though everything happened without warning. In reality, that instant is the result of a process so patient that it almost lies beyond human feeling. The two stars had to be born together. Both had to be massive enough to die as neutron stars. Their system had to survive two explosions. The orbit had to remain tight enough for gravitational waves to draw them together within the lifetime of the universe. Then physics had to complete the rest of the work, one orbit after another, through a depth of slowness that feels almost as though the darkness itself were closing the distance between them. There is a quiet beauty in this dance, because it does not need brilliant light to matter. In human life, we often notice the moments that shine: an explosion, a flash of lightning, a meteor, or a beautiful image in the sky. Yet many of the universe's greatest events are prepared by movements that are nearly invisible. Two neutron stars may orbit within a distant region of space without anyone knowing they exist. No civilization may be nearby to give them names. No eyes may watch each revolution. Even so, their orbit continues to change with perfect consistency, following laws that do not require an observer in order to exist. As the final stage approaches, the neutron stars are no longer simply two dense spheres circling each other. The tidal forces between them become immense. Each object stretches and distorts the other, even though neutron stars are extraordinarily dense and difficult to deform by ordinary intuition. Matter, in their outer layers, may begin to tear away. Magnetic fields, temperature, density, and relative motion combine to create an increasingly complex environment. The details of these final moments remain an active area of research through computer models, gravitational wave observations, and the light detected after collisions. For this journey, however, the essential point is that as the merger draws nearer, the system approaches conditions capable of releasing neutron-rich matter into space. We can think of the two neutron stars as reservoirs of matter locked tightly within gravity. While they remain separate, most of their neutron-rich material is confined inside those extremely dense stellar cores. It cannot easily escape and take part in the creation of heavy elements in open space. But when the two objects collide, the impact, tearing, and gravitational chaos can throw some of that material outward. This ejected matter becomes the environment in which the R process can unfold with extraordinary intensity. Gold is not created simply because neutron stars contain neutrons. It is created when the collision allows neutron-rich material to element, expand, cool, and pass through a rapid chain of nuclear reactions. This view helps us avoid a subtle but important misunderstanding. Two neutron stars are not like two enormous bars of gold colliding and breaking apart into golden dust. Nor are they spheres already filled with gold, waiting to scatter it across the universe. What they contain are extraordinary physical conditions: immense density, neutron, rich matter, and enormous orbital energy. During the merger, those conditions allow new atomic nuclei to be built. Gold is the result of nuclear processes occurring within the ejected material, not a treasure that was already stored inside the two dead stars. For most of the journey before contact, the orbiting neutron stars can be imagined as an extremely low and distant piece of music, far beyond the hearing of human ears. Its frequency changes with the orbit. Its rhythm grows faster as the distance closes. If there were a way to listen to space-time, we would not hear sound in the ordinary sense of air vibrating. Instead, we would detect another kind of signal, the shape of space itself stretching and contracting by an almost immeasurable amount, as gravitational waves pass through. It took humanity more than a century after Einstein's prediction to build instruments sensitive enough for this kind of listening. Through them, the dance of two stellar remnants became more than an idea inside an equation. It became something that could be detected from Earth. At this point, the two neutron stars have not yet collided. They are still orbiting, still losing energy, and still drawing one another into a tighter path. Yet the picture has already changed. What first appeared to be two cold stellar corpses in the darkness now emerges as a system accumulating meaning with every revolution. Within them lies neutron-rich matter, created by the deaths of massive stars. Between them, gravity is steadily narrowing the distance. From them, faint ripples are spreading through space-time. And ahead, as their dance reaches its final turns, the universe will release more than light. It will send us another kind of signal, finer than light and quieter than sound, yet strong enough to tell us that two stellar remnants are approaching their final encounter. Before humanity ever saw the light from a neutron star collision, the universe may already have sent out another sign, one far quieter. It was not light traveling into a telescope, nor radio waves, X-rays, or gamma rays. It was an almost immeasurably small stretching and squeezing of space-time itself. A delicate ripple created as extremely massive objects moved through an orbit that grew steadily tighter. As two neutron stars entered their final revolutions, each orbit did more than bring them closer together. It also made the space-time around them tremble, sending ripples outward in every direction, across the darkness between stars, through galaxies and intergalactic space, until an exceedingly faint part of the signal finally reached Earth. To understand this idea, we need to step gently into the way general relativity describes gravity. In everyday life, gravity is usually imagined as a pulling force. Earth pulls us toward the ground. The sun holds the planets in orbit. The moon draws the oceans into tides. That picture works well enough for many familiar experiences, but around extremely massive objects such as neutron stars, we need to look more deeply. According to Einstein, mass and energy curve spacetime, objects are not simply pulled through a fixed and empty space. They move through a spacetime whose shape has been bent by matter. A planet orbits a star because it follows a natural path through the curved region around that star. When two neutron stars orbit one another, the curvature changes continuously, and those changes can produce gravitational waves. Gravitational waves are not the same as sound, even though we sometimes use the word listen when describing them. Sound requires air, water, or some other material medium through which vibrations can travel. In the near vacuum of space, ordinary sound cannot travel very far. Gravitational waves, however, are vibrations of space-time itself, able to cross the universe without any air at all. As one passes through an object, it stretches the distance in one direction by an extraordinarily small amount and then compresses it, while the perpendicular direction changes in the opposite way. The effect is far too slight for any human sense to detect. If a gravitational wave passed through our bodies, we would hear nothing, see nothing moving, and feel no impact. Yet with instruments sensitive enough, its trace can be measured. The image of ripples on a lake is often used to suggest what gravitational waves are like, though it is only a bridge for the imagination. When a drop of water falls onto a calm surface, circular ripples spread outward. When two massive objects orbit one another in space-time, they also send ripples away, but these are not waves across a visible surface. They are minute changes in distance itself. We do not stand outside the universe, looking down on this imagined lake from above. We are inside it, along with our rulers, our planet, light, and every other object. Detecting a gravitational wave is therefore not like watching a wave move past our eyes. It is more like discovering that the ruler used to measure space has briefly been stretched and compressed by an almost imperceptible amount. For a long time, this idea existed only in theory. Einstein predicted gravitational waves in 1916 as a consequence of general relativity. But predicting that something exists is very different from being able to measure it. By the time gravitational waves reach Earth, they are so weak that they are nearly lost beneath the disturbances of ordinary life. Footsteps, traffic, geological movement, thermal vibrations, environmental noise, and even the faintest motions within the instruments themselves. To find them, humanity had to build enormous detectors capable of measuring changes in distance far smaller than the width of a proton. That scale is almost too small to hold in the mind, so it may be easier to imagine a vast scientific ear, quiet enough to hear a whisper from space-time passing through the noise of Earth. Those ears are gravitational wave observatories, such as LIGO and Virgo. LIGO uses two very long arms positioned at right angles to one another, with laser beams traveling back and forth between mirrors suspended with extraordinary care. When no gravitational wave is passing through, the relative lengths of the two arms remain stable in the way the instrument was designed to measure. When a wave arrives, one arm becomes very slightly longer, while the other becomes very slightly shorter, and then the pattern reverses. This changes the interference pattern of the laser light. Scientists do not see the gravitational wave directly. They read the trace it leaves in light, within a measuring system carefully protected from countless sources of outside disturbance. There is a quiet beauty in this method. To detect two distant neutron stars, humanity does not send a spacecraft toward them, collect samples from the collision, or simply wait for the first light to appear. Instead, we place long arms on Earth, use light to measure distance, and wait for a distortion almost too small to imagine. Somewhere far away, the universe trembles. Tens or hundreds of millions of years later, or longer depending on the source, the ripple reaches our small planet. For a brief moment, the distances inside the detector change by an infinitesimal amount, and the data records a curve. From that curve, scientists can infer the masses of the two objects, the way they orbit, the speed at which they approach one another, and the moment when they merge. The signal from two objects spiraling together has a distinctive shape. When the orbit is wider, the gravitational waves are weaker and lower in frequency. As the objects move closer, they circle faster, produce stronger waves, and send out signals at higher frequencies. When this data is converted into sound within the range of human hearing, it becomes a brief chirp, like a note sweeping rapidly upward. Science transforms an almost undetectable vibration into a symbolic sound that is easier for the human mind to grasp. It is not a real noise traveling through space, but a translation of space-time's rhythm into something closer to our senses. Within that short rising tone may be the entire final chapter of two dead stars that had orbited each other for an immense span of time. Before gravitational wave astronomy, our study of the universe depended mainly on light and other forms of electromagnetic radiation. Humanity first viewed the sky with the naked eye, then through optical telescopes, and later expanded its vision into radio waves, infrared, ultraviolet, X-rays, and gamma rays. Each form of light reveals a different layer of the cosmos. Radio waves show cold gas and vast magnetic structures. X-rays reveal intensely hot regions around compact objects. Infrared light allows us to see through dust and observe young stars. But there are events for which light tells only part of the story. Sometimes it is obscured, absorbed, delayed, or altered by the material around it. Gravitational waves opened another channel, not replacing light, but adding an entirely new way to detect the movement of extremely massive objects. For neutron star pairs, this new channel is especially important. Gravitational waves come directly from their orbital motion before and during the merger. They reveal the final dance even before the light from the ejected material can be fully analyzed. Light tells us about the hot debris, the kilonova, and the heavy elements being formed and decaying. Gravitational waves tell us about the masses, the orbit, the acceleration, and the moment the two objects make contact. When these two kinds of signals are placed side by side, the universe seems not only visible, but audible in a deeper sense. A distant event suddenly has two voices, one carried by light and another carried by the faint trembling of space itself. It is also worth recognizing the patience behind every detection. To find gravitational waves, scientists must filter out countless unrelated signals. A truck passing near a detector, a gust of wind, a distant earthquake, or a vibration within the equipment can all create noise. This is why observatories are located in different parts of the world. When the same signal appears in several detectors with the precise timing expected as a wave crosses the planet, confidence in the detection becomes much stronger. Scientists compare the data with patterns predicted by general relativity, searching for the curve that best matches a pair of black holes, a pair of neutron stars, or another possible source. The work is far quieter than the image of an explosion lighting the sky. Yet it is through this careful precision that the universe allows itself to be recognized. Within the story of gold, gravitational waves act as a kind of advanced signal. They do not directly announce that gold is being created in any simple sense. Instead, they reveal that two extremely dense objects are merging, and if those objects are neutron stars, the environment after the collision may be rich enough in neutrons for the R process to occur. The light of the kilonova then provides evidence of the ejected matter and the heavy elements forming within it. Only when these two signals are brought together does the picture become truly compelling. Space-time trembles as two stellar remnants collide, and then light from the heated debris reveals that a forge for heavy elements has opened in the darkness. We might imagine a night on Earth when detectors lie quietly in distant regions, lasers travel through long tunnels, mirrors hang in near-perfect stillness, and data flows through computers in tiny increments. No one hears an explosion in the sky. No flash appears close enough to illuminate the horizon. Yet within the data, a brief rising signal emerges, delicate and narrow, like a small stroke of ink on a very long sheet of paper. That mark may be a message from a place tens or hundreds of millions of light years away, where two neutron stars have reached the final turn of their orbit. The event may have occurred long before its signal arrived, but for the instruments on Earth, it becomes present in the moment it is recorded. That quietness reflects the way science sometimes transforms human understanding. Not every revolution begins with a brilliant image. Sometimes it begins with a curve in a dataset, a match between two detectors, or a signal so faint that years of preparation are needed before anyone can trust it. From that curve, scientists did more than confirm a prediction made by Einstein. They opened a way of observing the universe that does not depend entirely on light. Objects that once seemed silent in the darkness began to speak in a language of their own, not through sound, but through the way their motion distorts space. As two neutron stars approach the moment of merger, the gravitational wave signal grows stronger before reaching its briefest and most intense final stage. What remains afterward depends on the masses and specific conditions involved. The remnant may briefly become an extremely massive neutron star, collapse into a black hole, or pass through intermediate states that scientists continue to study through models and observations. But before the lay of the kilonova is seen, before telescopes begin searching the sky, gravitational waves have already announced that an extraordinary collision has been detected. They are like the first quiet knock on a door, faint but clear enough to turn the attention of the astronomical community toward the same region of the sky. From here, the journey approaches a very specific day in the history of modern science. A day when two neutron stars were no longer only objects described by theory or distant points inferred through pulsar observations. It was the day humanity both detected the trembling of space-time and saw light arriving from the same event. On that day, the story of gold moved beyond distant speculation and closer to direct observational evidence. After billions of years of cosmic preparation, more than a century after Einstein's prediction, and decades spent building enormous ears for spacetime, a signal passed through Earth and began the search for the light of a kilonova. On the 17th of August 2017, nothing on Earth seemed unusual in the course of ordinary life. The sky stretched wide as it did every day. Cities continued in their own restless rhythms. Oceans moved, trees stood in the wind, and people went about their small daily tasks without any sense that space-time had just delivered a message from very far away. But inside gravitational wave detectors, a signal appeared. It did not last long. It did not arrive like an explosion, shake windows, or move the ground in any way the human senses could recognize. It was a curve in the data, a delicate trace left by two extraordinarily dense objects spiraling toward one another in a distant galaxy. The signal was named GW170817. The first two letters stand for gravitational wave, while the numbers record the date of detection, the year 2017, the 8th month, and the 17th day. The name is brief and technical, yet behind it lies one of the most important moments in modern astronomy. By then, humanity had already detected gravitational waves from merging black holes. Those events confirmed that space-time could truly ripple in the way Einstein had predicted. But black holes, by their nature, do not usually produce easily detectable light when they merge in a relatively clean environment. GW170817 was different. The data suggested that the source was not a pair of large black holes, but two neutron stars coming together. And if that was true, the collision might produce not only gravitational waves, but light as well. Only a very short time after the gravitational wave signal, a faint burst of gamma rays was detected. Gamma rays are an extremely high-energy form of light, often associated with violent events in the universe. Their appearance at nearly the same moment drew even more attention. It was as though the cosmos had sent two signs from the same place. First, a ripple in space-time, followed by a flash of high-energy light. When these signals were considered together, the case for a neutron star merger grew much stronger. Almost immediately, a vast search began. Telescopes around the world turned toward the region of the sky from which the signal might have come. This was not as simple as looking at a star whose location was already known. Gravitational waves helped identify an area of sky, but that area was still broad enough to require the cooperation of many observatories. Astronomers had to compare new images with older ones, searching for a point of light that had only just appeared, an unfamiliar source already beginning to fade. In astronomy, discovery does not always come from staring at one place for a long time. Sometimes it comes from recognizing a very small change among countless points of light that look almost the same. Eventually, a new source was found in the galaxy NGC 4993, more than 100 million light-years from Earth. That is an immense distance on the scale of human life, though relatively nearby compared with many cosmic events studied by astronomers. The light did not come from an ordinary star, nor did it resemble a familiar supernova fading in the ways scientists had observed many times before. It dimmed more quickly and changed color over time, revealing the signature of a kind of transient glow that had already been predicted, a kilonova, the light produced by matter ejected during the merger of neutron stars. From that moment on, GW170817 was no longer only a signal recorded inside gravitational wave detectors. It became an event observed in many different ways at once. Gravitational waves described the motion of the two stellar remnants before they merged. Gamma rays revealed a burst of high-energy radiation connected to the collision. Optical and infrared light showed hot material expanding, cooling, and changing color. X-rays and radio waves, which appeared and evolved later, helped scientists understand more about material moving outward at nearly the speed of light. It was one event, but each type of signal told a different part of the story, adding another layer and allowing the picture to grow clearer with every passing day. What made the event especially important to the story of gold was the kilonova light. When neutron-rich matter was thrown out of the collision, our process reactions could unfold, creating heavy elements. Those elements did not remain entirely silent. As they formed and decayed, they heated the expanding material and caused it to glow. The light carried traces of matter in transformation, like luminous ink revealing that the universe had just written new heavy elements into space. In the observations that followed GW170817, the changing color and brightness were consistent with the idea that a large quantity of heavy elements had been produced in the neutron star merger. For science, this formed an essential bridge between theory and observation. Astrophysicists had already developed models suggesting that neutron star collisions could produce many heavy elements through the R process. But even the most elegant model must eventually be tested against data. GW170817 allowed humanity to detect gravitational waves from two neutron stars, locate the source in the sky, observe the kilonova, and then follow the way its light faded and changed color. For the first time, several different lines of evidence pointed toward the same story. Two neutron stars merged, neutron-rich matter was expelled, heavy elements formed, and the light from that process traveled all the way to Earth. The moment can be imagined as a scientific room in which several windows suddenly opened at once. Before this, humanity had studied the universe mainly through light. The detection of gravitational waves opened another window, allowing us to sense the motion of extremely massive objects without depending entirely on electromagnetic radiation. With GW170817, both windows looked toward the same event. Space-time trembled, light appeared, and data from observatories around the world came together to form a single story. Astronomy entered the era of multi-messenger observation, in which the universe was no longer studied through only one kind of signal. Within the slow rhythm of this journey, we can pause to notice the humility of the discovery. A collision more than 100 million light-years away had occurred long before its signals reached Earth. When the light and gravitational waves first began their journey, our planet was still moving through its own history. The signals then crossed space for an immense span of time, never hurrying, never stopping, and never knowing that on one small planet, a living species had built instruments delicate enough to recognize them. When those signals finally passed through Earth, humanity did more than detect a collision. It touched a distant chapter in the history of matter. GW170817 also changed the way we think about gold on Earth. Before the event, the idea that gold could come from neutron star mergers was beautiful, but still difficult to connect with ordinary intuition. Afterward, the story gained an observational foundation. No one saw individual gold atoms being created, because no telescope could isolate a single atom within an explosion so far away. But scientists did observe light consistent with the formation of heavy elements, emerging from exactly the kind of collision required by the theory. That transformed the story from a sweeping cosmic idea into a chain of evidence that could be followed step by step. The light of the kilonova faded quickly over the days that followed, but the data remained. Every measurement of brightness, every spectrum, and every signal recorded at a different wavelength became a small part of the event's lasting record. Scientists asked not only how bright it had become, but how its color changed, how rapidly the material was moving outward, how much mass the ejected debris might contain, and which heavy elements could have contributed to the light growing redder over time. The answers were not simple, because the material within a kilonova is highly complex, containing many heavy elements that absorb and emit light in different ways. Yet that very complexity was itself a sign that we were looking into an environment of extraordinary chemical richness. In everyday life, gold is often associated with stability. It does not tarnish easily or change readily, and it can pass through many generations while preserving nearly the same form. Yet its origin, viewed through the story of GW170817, is connected to a moment of almost unimaginable violence and brevity. There is a beautiful contrast here. One of the quietest metals in the human hand may carry the memory of one of the most chaotic events in the universe. Something so enduring that it seems almost motionless in daily life may have been born from matter torn away as two dead stellar cores merged. The 17th of August, 2017, was therefore more than the day a signal was recorded. It was a day when many layers of understanding came together. Einstein's general theory of relativity, the nuclear physics of the R process, astronomy conducted through light, models of neutron stars, and the ancient question of where the heavy elements came from all converged within a single event. Not every question was answered completely. Science continues to investigate how much different cosmic sources contribute to the total amount of gold in the universe. But after GW 170817, neutron star collisions were no longer a distant possibility confined to calculations. They had become a phenomenon that humanity had both heard and seen. From a quieter perspective, GW 170817 can be understood as a reminder that the universe sometimes reveals its greatest secrets through the smallest signals. No sound echoed across the sky. No streak of light appeared that an ordinary person could recognize with the naked eye. Yet, within the detectors, the telescope data, and the patient measurements of research teams around the world, an immense story emerged. Two stellar remnants that had orbited one another in darkness finally came together. Space-time trembled. Neutron-rich matter was thrown outward. The kilonova slowly faded after sending us traces of newly formed heavy elements. After this event, the question of gold no longer leads only toward distant theories. It leads to a specific day, a specific signal, a specific galaxy, and a network of telescopes and detectors that together recorded one of the most beautiful pieces of evidence for the way the universe creates heavy matter. But to understand what that light was telling us, we need to move closer to the nature of the kilonova itself. Not every bright explosion in the universe is the same. A kilonova has its own rhythm of fading, its own colors, and its own source of energy. And within that slowly vanishing light, the story of gold begins to come into clearer view. When two neutron stars merge, the light they produce is unlike the familiar stellar explosion we usually imagine. There is no massive living star tearing apart its outer layers after its core collapses, and no enormous fireball lingering with the rhythm of an ordinary supernova. This event begins with two dead stellar cores, far smaller than living stars, yet so dense that they lie beyond anything in ordinary experience. As they spiral together and reach their final moment, some of their neutron-rich matter is torn away and hurled into space at tremendous speed, expanding into a hot cloud that is changing from within. The light humanity sees from that cloud is called a kilonova. A kilonova can be understood as the light that follows the trembling of spacetime. Gravitational waves tell us that two extremely dense objects have merged. The kilonova reveals that some of the material was not completely swallowed by whatever remained, but was thrown outward, carrying the conditions needed to create heavy elements. Within this debris, atomic nuclei pass through an environment extraordinarily rich in neutrons. They can capture neutron after neutron, grow heavier, and then, through later decays, gradually become heavier elements on the periodic table. Gold, platinum, and many other heavy elements do not appear as ready-made pieces of shining metal. They form at the nuclear level inside a cloud of matter expanding at extraordinary speed. The light of a kilonova comes from the way this cloud cools and settles into greater stability. Many newly formed nuclei are not stable at first. They undergo radioactive decay, releasing energy that heats the surrounding material and makes it glow during the first days after the merger. We can picture the ejected debris as a cloud unfolding from the collision site, filled with countless nuclei searching for paths toward more stable states. Each small decay contributes a little energy to the shared light. The cloud expands, its temperature falls, its color changes, and its glow gradually fades, like the warm trace of newly created matter receding into the darkness. What makes a kilonova distinctive is the rhythm of its changing light. It usually does not remain brilliant for as long as many supernovae. At first, its glow may be stronger in blue or visible wavelengths, then quickly shift toward red and infrared as the material expands and cools, while also being shaped by the heavy elements that have just formed. These elements have complex electron structures, causing light to interact with the matter in more intricate ways. Some wavelengths are absorbed more strongly, while others escape later, changing the observed color over time. That shift is more than outward beauty. It is a clue that helps scientists read the composition and physical state of the debris after the collision. In the case of GW 170817, the source found in the galaxy NGC 4993 faded and changed color in a way consistent with a kilonova. At first, it appeared as a new point of light among countless others. Hour by hour and day by day, telescopes recorded its declining brightness, its shifting color, and the growing importance of its infrared emission. These changes matched the idea that neutron-rich matter had been expelled by the neutron-star merger, and that the R process had created many heavy elements within it. Humanity did not see individual gold atoms, nor did a distinctive golden streak appear in the sky. The evidence lay in the full behavior of the light, how it appeared, changed color, faded, and carried the signature of a cloud rich in heavy elements. The phrase, "the light of gold," must therefore be understood gently and precisely. A kilonova is not a mass of gold glowing in space. It is the light of a region where heavy elements are being created, potentially including gold, platinum, uranium, and many others. Gold does not stand alone within that light as an easily recognizable color. It belongs to a much broader nuclear story, mixed with countless other heavy elements that help determine how the expanding cloud absorbs, holds, and releases radiation. This truth does not make the image any less compelling. It gives the story greater depth, because gold is no longer merely a decorative detail, but part of the chemical maturation of matter. During the few brief days after the merger, that cloud carried a history unfolding at extraordinary speed. The two neutron stars may have taken millions or billions of years to reach their final encounter. Gravitational waves slowly drained energy from their orbit over a span of time almost impossible to feel. Yet once the two objects touched, matter was expelled, and nuclear reactions unfolded over a period extremely short, compared with the lifetime of a star. The kilonova shone as the visible part of that transition from matter once locked inside dead stellar cores to heavy atoms now free to drift through the galaxy. This contrast gives the story a rhythm of its own. Before the collision came an immense stretch of time, slow and nearly silent. Afterward came a brief period that was hot, bright, and filled with transformation. Then the light faded again, the cloud cooled, the new nuclei became more stable, and the material moved away from the event that had created it, becoming part of interstellar space. If gold formed within that debris, it did not immediately possess shape, a polished surface, or any value in the human sense. It existed only as newly formed atoms, drifting in an expanding flow of matter, belonging to no planet, resting in no mineral deposit, and untouched by any hand. Scientists do not read a kilonova through a single image. They follow it across many wavelengths, from visible light to infrared, then combine those observations with data from gamma rays, X-rays, radio waves, and gravitational waves. Each kind of signal answers part of the question. Gravitational waves reveal that two compact objects merged. Gamma rays suggest an accompanying flow of high-energy material. Visible and infrared light show the hot debris cooling and changing color. Later, X-ray and radio observations help explain the outflow and the way it interacts with its surroundings. It is one event, yet no single signal tells the entire story alone. The picture becomes clearer only when the different forms of data are placed beside one another. Through this method of observation, the kilonova became one of the most important lines of evidence for the origin of heavy elements. It is more than a beautiful glow following a distant collision. It is the trace of matter transforming itself, of nuclei capturing neutrons and then decaying, and of new heavy elements emerging in an environment that Earth cannot reproduce. From the outside, a kilonova may appear as nothing more than a small point of light slowly fading within a distant galaxy. Within the data, That point contains information about the speed of expansion, the composition of the material, the amount of mass expelled, and the role of heavy elements in shifting the light toward redder wavelengths. We can pause here for a moment and feel the difference between gold in ordinary life and gold at the place of its birth. On Earth, gold is associated with stability. It does not corrode easily, can preserve its shine over time, and survives within objects passed down through generations. Yet in its deepest origin, gold is connected to a moment of profound instability. Two dead stellar cores merging, matter being torn from the collision, nuclei capturing neutrons during a rapid transformation, and light appearing before fading again within a short span of time. One of the quietest metals in the human hand may carry the memory of a process that was anything but quiet. A kilonova also reveals that the universe does not create chemical richness through a single pathway. Some matter is formed within the cores of living stars. Some is dispersed when massive stars explode. Heavier elements require more extreme, neutron-rich environments, and neutron star mergers are one especially important source that has been observed directly. Parts of this story are still being studied because scientists continue to ask exactly how much of the universe's gold comes from neutron star collisions and how much comes from other sources. But after GW 170817, the kilonova was no longer only an idea within a model. It had become light that could be recorded, analyzed, compared, and used to understand how heavy matter can be born. From a small source of light in NGC 4993, humanity saw more than a collision. We saw one stage in matter's journey from extremity into stillness. First came the orbit of the two neutron stars. Then gravitational waves spread outward. The merger followed, releasing matter, triggering nuclear reactions, and producing the kilonova, which changed color and gradually faded. Yet as that light receded from view, the newly formed atoms continued to exist. They did not vanish with the brightness of the event. They became part of the interstellar medium, where gas and dust quietly mix over spans of time far longer than the light itself endured. That continuation carries the story beyond the moment of creation and into the long journey of dispersal. Any newly formed gold within the debris cloud would still be far removed from a ring, a coin, an ore deposit, or a planet. It would need to drift through space, mix into galactic dust, perhaps become part of another cloud of gas, and then wait for gravity to gather matter into a later generation of stars and planets. A kilonova is simply the place where light allows humanity to witness the birth of heavy elements. Their much longer existence begins after the glow has faded, as the cloud cools and the new atoms leave behind the violent event that created them, beginning their slow passage through the darkness between the stars. As the light of the kilonova fades, the story does not end in darkness. What disappears from the view of telescopes is only the event's most visible glow. The matter created and released after the merger continues to exist, expanding, cooling, and gradually blending into the vast environment between the stars. If gold is present within that material, it no longer remains in the fiercely hot region where nuclear reactions have just taken place. It becomes a collection of heavy atoms drifting alongside gas, dust, and microscopic fragments of matter, beginning a journey far quieter than the moment of its birth. We can imagine a cloud of material expanding into space after the collision. At first, it is hot, fast, and filled with energy. Newly formed nuclei are still decaying. Light is still escaping, and telescopes are still tracking the changing colors from one day to the next. But as the cloud travels farther from the merger site, it becomes increasingly diffuse. Its temperature falls. The violent reactions gradually subside. The material no longer shines brightly enough to be seen easily from Earth. To an observer, the event seems to have receded into the past. For the newly created atoms, however, one of the longest parts of the journey has only just begun. The space between the stars is not completely empty. It is so thin that, compared with the air around us, it is nearly a vacuum. Yet it still contains gas, dust, magnetic fields, cosmic rays, and extremely diffuse clouds of matter spread throughout the galaxy. Within this environment, atoms from the kilonova can blend into the surrounding material. They do not travel along a simple straight path like stones flying through empty space. They are carried by the broader motion of galactic gas, affected by shock waves from other stellar explosions, and mixed with matter released by stellar winds, supernovae, and many other sources. A galaxy is not a motionless room. It is more like an exceedingly thin ocean of matter, where broad and gradual currents continuously blend everything together over time. Newly formed gold from a kilonova does not appear as glittering grains of golden dust in the familiar sense. On a cosmic scale, it may exist as individual atoms or ions, or later become incorporated into tiny dust grains as the environment cools and chemical conditions allow. Interstellar dust is also very different from the dust found inside a room. It may consist of extremely small particles made of silicates, carbon, ice, metals, and many other compounds, far too small to be seen by the naked eye. A gold atom may become an almost immeasurable part of one such grain, producing no light of its own and carrying no distinct shape, quietly traveling with the larger material of the galaxy. This mixing requires immense spans of time. A neutron-star merger may create heavy matter in a brief interval, but for that material to spread into the interstellar medium, enter a new cloud of gas, and eventually become part of a later star system, everything must move according to the much slower rhythm of the galaxy. Gas clouds may be compressed by shock waves, pulled by gravity, stirred by the rotation of the galaxy, broken apart, and gathered again in different regions. A gold atom has no destination. It does not know that one day it may become part of a planet. It simply follows slow physical processes: motion, collisions, radiation, absorption, mixing, and gradual capture within denser regions of matter. At this scale, time becomes soft and spacious. A million years may be only a short interval in the journey of galactic gas and dust. Hundreds of millions of years may pass as matter becomes more thoroughly mixed across a broad region. Atoms created in a single event can spread outward and blend with material from many generations of stars. They may encounter carbon from aging stars, oxygen from massive stars that exploded, silicon forged in stellar interiors, and iron scattered by supernovae before all of them become part of a richer cloud. No element within that cloud displays its individual history in a way that can easily be seen. Yet each contributes something to the possibility of forming more complex worlds. This helps us understand why the solar system was not born from pristine matter. When the sun formed about 4.6 billion years ago, the cloud that gave birth to it contained more than the original hydrogen and helium of the universe. It had already been enriched by earlier generations of stars. Within that cloud were heavy elements created through many different processes: carbon, oxygen, magnesium, silicon, iron, nickel, and rarer elements such as gold. The solar system was therefore a place where old matter was gathered into new structures. The young sun formed mainly from light gases, while the heavier material entered the rotating disk around it, where dust grains collided, stuck together, and gradually grew into rocks, asteroids, and planets. A gold atom on this journey may have passed through many different states before becoming part of Earth. It may once have drifted freely through thin gas, then attached itself to a grain of dust, become enclosed within a small fragment of matter, entered an asteroid, and finally been drawn into the young planet through a series of chaotic collisions. There is no way to trace the actual path of a specific atom, but the larger picture shows that the heavy matter within Earth is an inheritance from events that occurred before the planet existed. Gold did not travel directly from a kilonova into an ore deposit. It passed through a very long sequence of transformations, with the galaxy serving as a region of mixing and the solar system becoming a later gathering of matter that had already been enriched. The story can easily be misunderstood here if we imagine that a single kilonova produced all the gold on Earth and delivered it directly to us. Science does not require such a simple path. The gold in the solar system may reflect many sources, many events, and many stages of mixing before the presolar cloud collapsed. Some of the material may have come from neutron star collisions, while other parts of the heavy element story remain under investigation. What matters for this journey is that neutron star mergers provide a real mechanism, observed through kilonovae, in which heavy elements can form and then enter the interstellar medium. From there, they can eventually become part of later star systems. When the kilonova's light fades, the quietness of the material does not mean that it has lost its significance. In the darkness between the stars, newly formed atoms do not need to shine in order to continue participating in the history of the galaxy. They need only to survive long enough, mix deeply enough, and be present at the right moment within a collapsing region of gas and dust. Gravity carries out its patient work. A vast cloud begins to contract. Denser regions draw in more material. A central core grows warmer, preparing to become a star. Around it, a disk of gas and dust rotates, while tiny particles collide, stick together, separate, and then join again. Heavy atoms, possibly including gold, enter this process as small but enduring components of solid matter. There is a special beauty in the fact that gold must pass through this unremarkable stage. At the moment of its creation, it is connected to an extreme event. In the human hand, it is associated with brilliance, value, memory, and symbolism. Between those 2 points lies an immense interval with almost no dramatic image at all, only gas, dust, slow motion, and quiet mixing throughout the galaxy. This middle passage makes the story feel more real. The universe does not carry an atom from its birthplace to its final destination along a clean and beautiful line. It allows matter to drift, meet, lose its separate identity, merge into larger currents, and then reappear within an entirely new structure. If a gold atom from a kilonova eventually became part of a dust grain within the presolar cloud, it would no longer carry any easily recognizable sign of the event that created it. It would have blended into a much larger mixture alongside countless atoms from many different sources. Much as a drop of water from a distant rainfall loses its separate boundary when it enters the ocean, a gold atom entering a star-forming cloud becomes part of a shared history. Yet, losing that boundary does not mean losing its origin. Within the chemical composition of the cloud, traces still remain of the events that once enriched the galaxy. From a distance, a galaxy may look like a faint band of light or a graceful spiral in an image. Yet within that beauty lies a system that is constantly recycling matter. Stars are born from gas. They transform matter within their cores. When they die, they return some of that material to space. Stellar remnants may collide, creating additional heavy elements and releasing them into the interstellar medium. Enriched again and again, clouds of gas and dust eventually give rise to new stars. Gold is only a small part of this vast cycle. It is not the center of a galaxy, but it is a sign that the galaxy has had enough time, enough generations of stars, and enough extreme events to become chemically rich. As the story leaves the kilonova and enters the wider galaxy, its rhythm slows. There is no longer a merger unfolding within seconds, no light changing color over a matter of days, and no urgent search by telescopes around the world. Instead, there are immense stretches of time, diffuse motion, and matter mixing almost invisibly. This is the stage when the universe is no longer creating gold, but carrying it onward. It moves those heavy atoms away from their birthplace, places them within the shared flow of galactic matter, and leaves gravity to decide when they will be gathered again. If traced far enough into the past, the gold in a ring carries not only the memory of a collision, but also the memory of the long wait that followed. That waiting leads to an important transition. A gold atom may drift through the galaxy for an immense span of time, but to become part of the familiar world, it must enter the process of star and planet formation. It must become part of a cloud of gas and dust, cold enough, dense enough, and unstable enough for gravity to draw inward. It must enter the disk of material rotating around a young star. It must be present within dust grains, small stones, and growing bodies that collide and gradually become larger. Eventually, it must be preserved inside a rocky planet, where geology will continue rearranging it over billions of years. The distance from the hot debris of a kilonova to a gold deposit deep underground is immense, not only in space, but also in the kind of story being told. What came before was the story of formation. This is the story of dispersal. The next part will carry that matter into a place closer to home. The cloud that gave birth to the sun, the disk of dust surrounding the young star, and the early Earth gathering the materials of the galaxy as it became a planet of rock, metal, water, atmosphere, and a very small amount of gold hidden within its body. About 4.6 billion years ago, in a region of the Milky Way that seemed no more remarkable than billions of others, a cloud of gas and dust began to collapse under gravity. This was no longer the pristine matter of the young universe. It already carried traces of many earlier generations of stars, stars that had been born, had shone, and had died long before. Within that vast mixture were hydrogen and helium, but also carbon, oxygen, silicon, iron, and rarer heavy elements, created in extreme events of the distant past. Some gold atoms may have spent hundreds of millions of years, perhaps even longer, drifting through the galaxy before becoming part of the cloud that was preparing to give birth to a new star system. As the cloud contracted, most of its material gathered toward the center. The temperature rose, the pressure increased. A young star began to form. It would eventually become the Sunday. The material that did not fall directly into the center continued circling the newborn star in a broad disk of gas and dust. Within that disk, countless small particles collided again and again. Most collisions produced nothing remarkable. Some particles stuck together. Larger clusters formed, then continued gathering more material. Over millions of years, small rocks grew into larger bodies and then into protoplanets, competing for material within the same rotating disk. If we could view that disk from far away with time greatly accelerated, it would not resemble an orderly construction site. It would be a chaotic place where young celestial bodies constantly collided, merged, or broke apart. Many did not survive. Some became asteroids. Some were thrown out of the system. Others grew into planets. Earth emerged through this process. It did not appear fully formed on a single day. It grew gradually through countless collisions, gathering material from its surroundings, while enduring impacts powerful enough to reshape its internal structure. During its earliest stages, the young Earth was far hotter than the familiar world of today. Heat generated by collisions, radioactive decay, and the process of planetary formation left much of its interior molten or nearly molten. Because matter could move relatively freely, elements began separating according to their density and chemical properties. Iron and nickel, both heavier than many other components, tended to sink into deeper regions. Over time, they helped form the planet's metallic core. This was a crucial stage in the story of gold. Under the conditions of the early Earth, gold tended to follow iron-loving elements. That means a significant portion of the planet's original gold did not remain near the surface. It may have been drawn deep into the interior along with the material forming the core. Following that logic alone, most of Earth's gold today might be expected to lie far beyond human reach. This led scientists to an intriguing question. If gold tended to sink toward the core while the young Earth was molten, why does the planet's crust still contain enough for humans to mine? The answer most likely involves a period of intense bombardment after the core had largely formed. During that time, many asteroids and smaller celestial bodies continued striking Earth. They carried new material from space, adding more elements to the planet's outer layers. Some of the gold now present in the crust may be connected to this late-arriving material. Although the precise details are still being studied and refined, the overall picture is fairly clear. Earth did not create gold. The planet inherited it from matter that had already existed within the galaxy. After Earth formed, geological processes determined where the gold would remain, how it would become concentrated, and whether it might one day appear close enough to the surface to be found. In other words, the nuclear origin of gold belongs to the wider universe, while its distribution belongs to Earth's own history. During the planet's first several 100 million years, Earth was still a world very different from the one we know. There were no forests, no stable oceans like those of today, and no living creatures looking toward the sky. Yet gold atoms were already present somewhere within the planet's material. They had no special shape. They did not glow to announce their presence. They were simply a minute part of Earth's enormous mass as the planet slowly cooled, separated into layers, and prepared to enter the longer chapters of its geological history. As the crust formed and tectonic activity began to play a greater role, matter within the planet no longer remained entirely still. Tectonic plates moved, volcanoes became active. Hot, mineral-rich water traveled through deep fractures in the rock. Under certain conditions, gold could be transported from one place to another while dissolved in high-temperature fluids. When those conditions changed, the gold settled out alongside other minerals, gradually forming veins of ore that humans would discover billions of years later. These processes unfolded with extraordinary slowness. A vein of gold does not appear within a few years or even a few centuries. It is the result of geological history, extending across spans of time the human mind cannot easily picture. While our civilization has existed for only a tiny fraction of Earth's history, many gold deposits began forming before animals lived on land, and in some cases, even before multicellular life had appeared. There is an intriguing contrast between the way gold is created and the way it becomes concentrated. Its nuclear origin is connected to extremely brief and violent moments in the universe. The geological origin of a gold deposit, however, is tied to processes that are slow and quiet. On one side are neutron star collisions, gravitational waves, and kilonovae. On the other are hot fluids moving through rock, tectonic plates shifting by only centimeters each year, and chemical reactions continuing for millions of years. These two stories move at entirely different rhythms, yet they ultimately meet within the same atom. When we think of a gold ring resting on a table, very few of us imagine the distance its material has traveled. Before it lay within the rocks of Earth, it was part of the interstellar medium. Before drifting between the stars, it may have formed within matter expelled by a neutron star merger. Before that event came the lives of massive stars that died and left neutron stars behind. A small object from everyday life can therefore contain a history older than the planet, older than the sun, and reaching back into some of the earliest chapters of the galaxy. What makes this story memorable is not simply that gold is precious. Any other element created along a similar path would have a remarkable journey of its own. Gold merely helps us recognize a broader truth. The matter around us did not begin where we found it. An atom buried in the ground may carry the memory of regions millions of light years away. An object resting quietly in the hand may once have taken part in violent events that Earth did not yet exist to witness. At this point in the journey, gold has traveled from a kilonova into the galaxy, from the galaxy into the presolar cloud, from the disk of dust surrounding the young sun into the early Earth, and then from matter deep within the planet into ore veins shaped over geological time. Only one final step remains before the story reaches the human world: how atoms born from the deaths of stars became part of civilization, technology, art, and the memories and meanings we now attach to them. After traveling through the most distant layers of the story, from the merger of two neutron stars to the light of a kilonova, and from interstellar dust to the cloud that formed the solar system, gold finally returns to a much closer setting: the human hand. There, it is no longer seen as a single atom drifting through the galaxy or a tiny component hidden inside rock. It becomes a ring, a coin, A sheet of gold leaf, a necklace, an electrical contact, a symbol, a memory. Matter that has passed through an immense cosmic history begins another kind of life, shaped not by nuclear reactions, but by the meanings human beings give to it. Earth contains many metals, yet gold has held a special place in nearly every civilization that came to know it. Part of that comes from its appearance. Gold has a warm and unusual color that sets it apart from most familiar metals. Iron may be gray, silver bright and white, copper closer to red, but gold carries a stable golden tone that is easy to recognize. Under low light, it does not need to shine intensely to draw attention. It reflects a warm, rich, gentle glow, as though it holds onto a little light without immediately giving all of it back. From very early on, this quality helped connect gold with the sun, endurance, power, and the things people hoped would last beyond their own lifetimes. Another reason lies in gold's chemical properties. It does not oxidize easily like iron, nor does it quickly tarnish, decay, or break down under ordinary conditions. An object made of gold can pass through many years while preserving its familiar brightness. This made it especially distinctive in the ancient world, when many materials changed color, wore away, rotted, or lost their shape with time. Gold seemed less willing to surrender to changes on its surface. Ancient people did not know about electron structures or electrode potentials, but they could see that gold endured longer, suffered less damage, and carried something close to the feeling of permanence. Gold is also soft and easy to work. It can be hammered into extremely thin sheets, drawn into wire, bent into shape, engraved, melted, and cast again without losing its essential nature. For human beings, this was an important quality. A material that was rare but nearly impossible to shape might never have entered culture in the same way. Gold was rare, beautiful, and workable enough for human hands to give it meaningful forms. It could rest on a crown, cover part of a statue, appear in a ritual, become a small piece of jewelry, or serve as a keepsake passed from one generation to the next. But gold remained with humanity for more than its beauty. It is both rare and not impossibly rare. If it were as common as ordinary stone, it would be difficult for it to feel special. If it were so scarce that almost no one could find it, it could never have become such a large part of cultural history. Gold occupies an unusual middle ground, rare enough to be valued, durable enough to preserve, recognizable enough to become a symbol, and workable enough to enter everyday life. This balance allowed it to serve as a medium of exchange, a store of value, a mark of power, an ornament, and a material in many forms of modern technology. Here, the scientific story meets the human story in a natural way. The universe made gold rare through the difficulty of creating it. Earth made it difficult to find by burying it in rock, drawing much of it deep into the planet, and allowing only a small portion to become concentrated near the surface through slow geological processes. Human beings made it meaningful by connecting it with value, memory, identity, love, power, inheritance, and sometimes greed. The atom itself does not change, but as it passes through different layers of history, it gathers different layers of meaning. A gold ring, therefore, has two lives unfolding at once. The first is its material life. The atoms within it have a specific number of protons, a particular nuclear mass, and an origin in distant cosmic processes. The second is its symbolic life. The ring may mark a promise, a relationship, a family memory, a separation, a reunion, or simply an object someone has chosen to keep close. Science does not erase this second layer of meaning. It places something deeper beneath it, allowing us to see that what people give to one another is made from matter that has passed through a history far greater than any human life. In modern technology, gold has another life, less poetic but entirely real. It conducts electricity well, resists corrosion, and remains stable under many conditions, which makes it useful in electronic connectors, precision instruments, satellites, medicine, and countless small applications that often escape notice. A very thin layer of gold inside a device may have none of the appearance of jewelry and may never rest inside a velvet-lined box. Yet, it depends on the same qualities that make gold valuable: durability, stability, low reactivity, and reliability in places where long-lasting contact matters. Gold inside a circuit does not tell the same romantic story as a ring, but it is still cosmic matter serving the delicate needs of a civilization capable of building tools. The longer we look, the more gold becomes a meeting point between vastly different scales. At the nuclear scale, it is the result of protons, neutrons, and the processes that form heavy elements. At the astronomical scale, it is connected to neutron stars, kilonovae, interstellar dust, and the formation of planets. At the geological scale, it is carried by hot fluids, buried in rock, lifted upward, eroded, and concentrated again. At the social scale, it enters trade, art, ritual, technology, and personal memory. Something so small can connect scales separated by almost unimaginable distances, from the atomic nucleus to the hand of a craftsperson, from the galaxy to an object resting quietly inside a drawer. This also reminds us to be careful with the word precious. In everyday life, preciousness is often connected to price, rarity, the ability to preserve value, or social status. In science, gold is precious in a quieter sense. It is the trace of a sequence of conditions that are difficult to reproduce. Not because the universe favors gold over other elements. Every element has a story of its own. Carbon carries the story of life. Oxygen carries the story of water and breath. Iron carries the story of planetary cores and blood. Gold carries the story of neutron-rich environments and heavy matter created and preserved through time. Seen this way, its value lies not only in markets or symbols, but in its ability to reveal the history of matter. Perhaps this is why gold so easily becomes a small mirror for the way human beings look at the universe. We usually begin with what is closest: a ring, a piece of jewelry, an old coin, a family keepsake. Then the question gradually expands. Which mine did it come from? Which layer of rock? Which geological age? Which presolar cloud? Which cosmic event? The farther back we travel, the more the object loses its familiar meaning, yet gains another kind of depth. It is no longer only the possession of a single lifetime. It becomes a small point where many histories meet. The story of gold should keep this balance. There is no need to turn it into something mystical beyond science, and no need to reduce it to a metal with economic value. The most beautiful view lies between those two extremes. Gold is a real element, with real chemical properties, a real nuclear origin, a real geological journey, and then a place within the very real stories of human life. Its wonder does not come from distorting the truth, but from the fact that the truth is already vast enough. A gold atom does not know that it is precious. Human beings are the ones who look at it, preserve it, exchange it, and then realize that a fragment of the ancient universe may be held within something so small. From this perspective, a gold object resting beneath a lamp is no longer entirely silent. It does not speak through sound, but if we pay attention, it suggests many layers of time. There is the brief time of the hand holding it. There is the time of a family, of memories, and of the people who kept it before. There is the time of ore deposits, mountains, and hot water once moving through fractures in rock to gather the gold together. Farther back lies the time of the solar system and the cloud of gas and dust that formed Earth. Farther still lies the time of neutron stars, kilonova light, and matter thrown outward before drifting across the galaxy. Each layer does not erase the one before it, but adds greater depth to the same object. This is why gold remains with humanity, not only because it resists the air or looks beautiful in light. It remains because it allows people to place the small events of life within a much larger frame of time. A wedding ring may belong to two people in a deeply private moment, but the matter within it belongs to a history that is no one's private possession. An ancient coin may record the memory of a kingdom, yet its atoms are older than every kingdom. A thin layer of gold inside an electronic device may serve modern technology, but it is made from matter that existed long before humanity appeared. From here, the journey moves into a broader layer of modern science. Gold helps us tell the story of where matter came from, but the discovery of kilonovae and gravitational waves has done far more than that. It has changed the way humanity observes the universe. In the past, we studied the sky mainly through light. Today, we can also listen to the faint ripples of space-time and combine them with visible light, gamma rays, X-rays, and radio waves to understand a distant event through several signals at once. The story of gold therefore opens a larger door, multi-messenger astronomy, where the universe is not only seen, but recognized through many different ways of carrying information. For most of the history of skywatching, humanity came to know the universe primarily through light. At first, it was the light visible to the naked eye, the moon, the planets, and the faint Milky Way stretching across the night like a river of milk. Later, that light was gathered through telescopes, magnified, separated into spectra, and measured with instruments far more sensitive than the human eye. Gradually, astronomy expanded beyond visible light. Radio waves revealed cold gas and vast regions of the galaxy. Infrared allowed us to see through dust. X-rays exposed intensely hot matter near extreme environments. Gamma rays carried news of high-energy outbursts. Each kind of signal became a window of its own, allowing humanity to observe the same universe at different depths. Gravitational waves added a window unlike any form of light. They are not electromagnetic radiation, and they do not arise from moving electrons or glowing atoms. They come from the motion of large masses through space-time, especially when extremely dense objects spiral around one another at tremendous speed. When detectors such as LIGO and Virgo record gravitational waves, they do not capture an image in the ordinary sense. They measure an almost immeasurably small change in distance, then use that change to reconstruct the story of distant objects. The universe, once observed mainly as a picture made of light, began to reveal a rhythm of its own. The combination of several kinds of signals is known as multi-messenger astronomy. The phrase is especially fitting when we think of each messenger as a form of information traveling across the universe. Light is one messenger. Gravitational waves are another. Neutrinos, particles that pass through matter almost without leaving a clear trace, can also serve as messengers in certain events. Each one leaves its source in a different way, is affected differently by the environment along its path, and arrives at Earth carrying a different part of the story. When several messengers are detected from the same event, we no longer have to rely on a single clue. We can bring the pieces together, like listening to several witnesses describe the same moment from different positions. GW 170817 remains one of the most powerful examples of this kind of observation. Gravitational waves arrived first, revealing that two compact objects were merging. At almost the same time, gamma rays were detected, suggesting an accompanying burst of high-energy material. Telescopes then found a new source of light in the galaxy NGC 4993. That glow was followed across many wavelengths, including visible light, infrared, X-rays, and radio waves. No single signal told the entire story. The gravitational waves described the orbit and the masses. The kilonova light revealed the ejected material and the formation of heavy elements. Gamma rays, X-rays, and radio waves helped expose high-energy outflows and the way they interacted with the surrounding environment. Through that coordination, the neutron star merger became more than an event heard through space-time or seen through light. It became a story with depth. We learned that two extraordinarily dense objects had spiraled together. We identified the specific galaxy where the event occurred. We learned that matter had been thrown outward. We followed the light as it changed color, faded, and shifted into the infrared. We saw evidence consistent with the creation of heavy elements. From one distant event, many layers of data came together to form one of the clearest pictures yet of how heavy matter can be born in the universe. Each messenger arrives at a different time and carries a different kind of information. Gravitational waves come from the orbital motion before and during the merger, passing through gas and dust with almost no obstruction. Light comes from the hot matter after the collision and is shaped by its chemical composition, temperature, density, and the direction in which it is expelled. Gamma rays may be connected to narrow, rapidly moving streams of high-energy material. X-rays and radio waves may appear later, when those outflows strike the surrounding environment. Taken together, these signals provide more than a single image. They create a timeline of the event, the period before the collision, the immediate aftermath, and the days and months that follow as the material continues to spread outward. This way of observing also changes how the sky feels to us. In the past, a dark region might have seemed completely quiet if no visible light stood out. Now we know that unseen motion may be taking place within that darkness, that ripples in space-time may be passing through, that nearly invisible particles may be crossing the planet, and that faint radio signals may be arriving from distant matter. The sky is more than a screen made of light. It is filled with many kinds of messages, each requiring its own scientific sense to be recognized. The beauty here does not lie in the noise of technology, but in the subtlety of listening. Gravitational wave detectors must distinguish an unimaginably small distortion from the countless vibrations of Earth. Telescopes must find a rapidly fading point of light among millions of other sources. Scientists must compare timing, position, signal shape, intensity, color, and physical models. An event in a distant galaxy does not speak in one complete sentence. It sends separate fragments. A faint ripple, a brief flash, an optical point of light, an infrared glow, and a delayed radio signal. Humanity must be patient enough to assemble them into a meaningful story. Multi-messenger astronomy also keeps the story of gold from standing alone. If we simply say that gold comes from neutron star collisions, the event may seem isolated, and the story may end there. But when we place it within a network of signals, we see more clearly that the origin of gold is part of the way the universe communicates information to us. Gravitational waves confirm the meeting of two stellar remnants. The kilonova reveals traces of heavy matter. Spectra and light curves allow nuclear models to be tested. Together, they connect the story of matter with the story of observation. Gold is not only the product of a distant process, it is also one reason humanity learned to perceive the universe through several channels at once. Since GW 170817, scientists have continued waiting for more events of the same kind. Each new neutron star merger may help answer questions that remain open. Does every neutron star merger produce a kilonova bright enough to be seen easily? How does the composition of the ejected material change with the masses of the two neutron stars? How many heavy elements are produced in each event? How much do neutron star mergers contribute compared with other cosmic sources? These questions do not weaken the discovery made in 2017. They show that it was a doorway, not a final wall. For a video meant to be heard before sleep, this part of the story can settle into a very quiet image. In many places across Earth, instruments are still waiting patiently for signals. The long arms of gravitational wave detectors lie across open stretches of land. Telescopes face the sky, sometimes receiving light that has traveled for millions of years. Satellites watch for gamma rays, X-rays, and infrared light. Each instrument is like a highly specialized sense belonging to humanity, neither loud nor hurried, simply open and waiting for another fragment of information from the universe. While people sleep, the data continues to flow. As city lights dim, the sky continues sending its faint signals across space. That stillness does not make science any less extraordinary. It brings science closer to the act of listening. We do not force the universe to tell its story in the way we prefer. We build instruments, ask questions, wait, and learn how to read the signs the universe actually sends. Sometimes the messenger is light. Sometimes it is a gravitational wave. Sometimes it is a delayed signal in the radio spectrum. Sometimes the absence of a signal helps rule out possibilities that are wrong. Each fragment makes our understanding clearer, not through hurried certainty, but through a slow and patient accumulation of evidence. Within this larger picture, gold becomes a thread connecting many fields of science. It belongs to nuclear physics because we need to understand how atomic nuclei capture neutrons and decay. It belongs to stellar astronomy because we need to understand where neutron stars come from. It belongs to general relativity because gravitational waves provide evidence of the merger. It belongs to multi-wavelength observation because kilonova light is studied across many regions of the spectrum. It also belongs to geology and the history of Earth because atoms created far away must eventually be gathered into a planet and concentrated within rock. A small ring may stand at the end of this chain, but behind it lies the combined work of many branches of science. The deeper we go, the more we see that the story is asking more than simply, where does gold come from? It asks a broader question. How do human beings discover the origin of anything in the universe? We cannot travel backward through time and stand beside two neutron stars. We cannot carry an instrument to a kilonova, collect samples, and bring them home, nor can we watch the journey of each individual atom from a distant galaxy to Earth. What we have are signals, models, measurements, comparisons, and the patience to connect separate pieces. Science does not erase the distance between humanity and the universe, but it builds delicate bridges that allow understanding to cross. Those bridges are what make the story of gold more memorable than a simple answer. If we say only that gold can be created when two neutron stars collide, we have a compelling fact. But when we go farther, we begin to see how that fact was discovered. Einstein's prediction, gravitational, wave detectors, telescopes around the world, kilonova data, models of the R process, and analyses of light changing color over time. The answer becomes deeper because we understand not only the result, but also the path humanity followed to reach it. After the signal detected in 2017, what remained was not a final period, but a new region of the sky that needed to be heard more carefully. Gold has carried us through the origin of the elements, the deaths of stars, gravitational waves, kilonovae, and multi-messenger astronomy. But good science does not stop at the most beautiful answer. It also preserves what is still unknown, the limits and the questions that remain open. Neutron-star collisions are an important source of heavy elements, a conclusion strongly supported by observation. Yet the complete story of all the gold in the universe is still being assembled, and that unfinished space keeps the journey from closing too soon. As evidence grows, science becomes more careful with answers that seem too simple. When we return to the image where this journey began, a piece of gold resting quietly beneath soft light, it may no longer seem exactly as it did before. Its surface is unchanged, still warm, still luminous, still silent in the human hand. Yet behind that silence, we have now seen a far greater history, a young universe, with almost no gold, the first generations of stars beginning to enrich matter, massive stars reaching the ends of their lives and leaving dead cores behind, two neutron stars orbiting each other in darkness, gravitational waves traveling through space-time, the fading light of a kilonova in a distant galaxy, and heavy atoms drifting through stardust before becoming part of Earth. Gold did not begin as a ring, nor did it begin in a mine, a riverbed, or the hands of a jeweler. Those places are only late stopping points in a journey older than the planet itself. Before human beings named it, valued it, gave it away, or kept it safe, gold was already matter belonging to the galaxy. It had passed through processes that no civilization could witness from beginning to end, across spans of time so immense that all of human history appears only as a thin mark near the bottom of the page. Perhaps the deepest beauty of this story lies not in the rarity of gold, but in the way it connects scales that seem impossibly far apart. A tiny atom can lead us into nuclear physics. A piece of jewelry can open a question about neutron stars. A faint glow in a distant galaxy can help explain some of the matter hidden beneath the ground. The near and the far, the softness of human memory, and the violence of the universe are not as separate as they may seem. They meet within matter, in atoms that quietly endure through time. If one idea remains after this journey, it need not be that gold has become more mysterious, but that scientific truth is already beautiful enough. The universe does not need to turn gold into magic. It needs only gravity, time, stars that live and die, stellar remnants that meet again in darkness, nuclear reactions unfolding within a brief and extreme moment, and clouds of dust drifting patiently through the galaxy. From all of this, a heavy element can be born, survive, disperse, become gathered into a planet, and one day rest quietly in the hand of a person wondering where it came from. And as the night grows deeper, as the light around you softens, the story can remain in one very small image. Within every piece of gold is a trace of stars that have died. Within the stillness of an object held in the hand is the distant trembling of space-time. And within what human beings call precious is a history far greater than any value we have ever placed upon it. The universe is not only out there, far beyond us in the sky. A very ancient part of it has traveled through time to become the matter around us, quiet, enduring, close enough to touch, yet deep enough to remind us that even the smallest things can carry the memory of a very distant night